Ok, ok. Tá ok, Vinícius? Dá para ouvir? O LEDzinho fica modulando, verdinho? Então tá entrando o som. Obrigado.
Well, hi everybody, good afternoon. We have here the lecture of Professor John Baldwin. Professor Baldwin is an emeritus professor at the UIC, Chicago, University of Illinois at Chicago, and he gives his name to the theorem that maybe some of you know, the Baldwin-Lackland theorem, which is a textbook theorem in model theory. Once a professor told me that his criteria for a good mathematician is that to have a theorem in a standard graduate textbook of mathematics. Professor Baldwin meets this criteria. Right? He has a theorem in standard logic textbooks. So we will have the pleasure to attend his lectures on axiomatization of geometry and the subject of definitions. So thank you, Professor Baldwin.
Thank you. Are you hearing? Yeah. It's a pleasure to be here. Are you hearing the mic? Okay. So yeah, it's a pleasure to be here. I've found Sao Paulo a very nice place. And this got started when I was corresponding with Rodrigo about the work he's going to be talking about. And exactly how close the connections are, we'll discover in the next week. And this work, well, I've got the titles rather than them. You'll see that there's a very strange things here. And so there's going to be a connection mostly with the history of geometry. And on a philosophical side, what concepts are and how they develop over time. And not on this set of slides, but a contribution with a new logic that establishes, for example, categoricity of piano arithmetic because of a new rule. But that saying it's about arithmetic is wrong. It's a new logic, and we characterize those countable structures which are categorical, and one of them is arithmetic. So I'll just move on to the actual topic. So what I'm trying to do is look at the development of concepts over the last 2,300 years. And I'm going to start about Euclid and move on to Descartes and Hilbert. And eventually some connections with the Moïse, well, the Berkhoff, Moïse is the popularizer. And worrying about how one can characterize formally as opposed to informally. I'll give you a sort of schema of what kinds of frameworks mathematicians are working in or people are thinking of in various times. And I have to mention Andreas Müller, who is my co-author with several papers on the geometry. He's a high school teacher. Well, he's retired as well, but retired a little younger, but retired. And Constantin Brinkas, who is a young philosopher in Romania and introduced me to inferential logic about 2 years ago, and that plays a big role. And one of the lectures will be basically about that, but the philosophical thing starts pretty shortly and also is heavily indebted to him. So it's going to be pretty informal. I've got probably more material that I'm going to get to, but I don't know where. That's why the first one is called 1 or 2, because it's designed that we'll quit wherever we get to. And we want to have conversations, so if we don't get through everything, as I go along, I'll try to specialize to the things that are actually people are interested in. Oh yes, I've got this device. So, as I said, this is about concepts, and that's something people have been fighting about, I suppose, since Aristotle at least. And Constantine gave this note. Concepts are what they are and nothing else. Just an instance of the principle of identity. So true in all frameworks. Where frameworks is a technical phrase, I'm going to tell you 4 of them in a few minutes. He quoted naming and necessity, Kripke, quoting somebody else. Every object is what it is and nothing else. And Kripke quotes this for saying that some notions, for example, reference, cannot be explained by reducing it to some other notions. But when they say what it is, or what they are, I think you can analyze what that R means. And so that's what I'm going to be doing. And so I do think of concepts as being mental objects. I mean, I'm not going to get stuck in any worries about Plato. I mean, sometimes I think, well, we can't possibly have invented this stuff if we've discovered it. But on the other hand, what has happened in history is people have these concepts, they develop, they change, and that's the kind of notion that I want to talk about. But then there's something in the mind that is being communicated. Somehow or the other, you understand what I'm saying. So individuals hold concepts, but they aren't all the same. We will have slight differences, and maybe more than slight. Well, I guess that's the next slide. No, let's just say. More precisely, a concept is a pair. There's some sort of label and what its meaning or content is. And since I'm going to talk about lines from Euclid to Dedekind is maybe a good example, they've got very different notions of what a line is. And so if I were really being precise, I'd go putting them in a bunch of subscripts, but That's too much typing for me. And we're going to organize this, and here again is where I'm indebted to Constantine, the notions of kinds of frameworks of where a particular discussion is taking place. And in particular, we'll talk about various systems of organizations, various kinds of logics. Actually, formalism, freeness, and category theory are there as things that aren't going to be talked about, but are in the general theme. And I'm only going to be talking about basically plane geometry. Nothing. I don't think anything much would happen if you went to higher dimensional geometry, but Euclidean, non-Euclidean geometries are close, and the same sorts of thing would work, but that's not the examples I'm going to give. And I think I've got one just side story that just appeared, and I've got another one that I'll get in a few days because I just got the book yesterday, or just remembered to read the book yesterday. But Viktor Verbovsky is a Kazakh with whom I've written a couple of papers, and a couple of days ago he sent me a paper called something like a book called In the Beginning the Set Was Empty, which is a very humorous idea about the developments of concepts in set theory, and is in some sense it's the same story, same kind of story I'm trying to tell, but in an entirely different genre. And I thought people might be interested in it. Okay, so this is, at some point I was interested in the role of Bourbaki in the development of 20th century mathematics. And there were many of the mathematicians have been unwilling for a long time to see in axiomatics anything other else than a futile, logical hair-splitting, not capable of fructifying any theory whatsoever. And while they say other mathematicians, they really are talking of themselves. The critical attitude can probably best be accounted for by a purely historic accident, namely that the first axiomatic treatments, and those which caused the greatest stir, those of arithmetic by Dedekind and Peano, those of Euclidean geometry by Hilbert, dealt with univalent theories, theories which are entirely determined by their complete system of axioms. So we're going to call that categorical now, but Bourbaki's, that's actually a good word. And for this reason, they could not be applied to any theory except the one from which they had been abstracted, quite contrary to, for example, to what we have seen for groups. If the same had been true of all other structures, the reproach of stability brought against the axiomatic method would have been fully justified. Well, so they realize, and then in the rest of their tirade, the hypothesis of the last sentence is false. It's not true for all other structures, and it's only true of things like arithmetic if you choose a logic that makes it true. And so, not surprisingly, well, this was probably written in the 40s, but for people whose beliefs were formed in the 20s, they don't understand the role of different kinds of logics. And so they miss the distinctions between axiomization and theory, and or the distinction between first and second order logic, or now all the different model-theoretic logics for which they can't be blamed. Right? I mean, that's quantifiers like there exist uncountably many are a product of the 60s, I guess. And just going, they ended this up with, we emphasize that logical formalism is one aspect of the axiomatic method, and indeed the least interesting one. And I kind of reverse it. The axiomatic method is but one aspect of logical formalism, and the foundational aspect of the axiomatic method is the least important for mathematical practice. Now, we aren't actually going to get into that here, but it's in the, that's what a lot of my book where this comes from. So 2 rules of formalization. One is sort of the foundational notion, and the other is, so here I was thinking, this was written specifically thinking about first-order logic. When mathematics is organized by studying first-order complete theories, syntactic properties of the theory induce profound similarities in the structures of models, and these are tools for mathematical investigation. And of course, here I should have put up Conant's diagram of the geography of mathematics under the classification theory. That's what I'm talking about. So let's go back to the beginning. Now, this is where the material you have is beginning. And I'm going to say a couple of things about it, and then we can chat about it for a while. So here are some of the first 10 definitions in Euclid. And one of the things I want you to think about is, I sort of separated these to ones that I think have sort of different meaning, different functions, and think about what that is. And Hilbert now has axioms where certain things are not defined. Well, Euclid, well, sort of defines everything. And these are the axioms. And then he gives also a definition of what it means to be, what a line segment is, I guess. And how does that notion of definition differ from what we had on the previous page? And then he has the common notions, which I think sometimes they call them axioms, but we really want axioms to be Euclid's postulates. And so these are general properties, right? There's nothing said about lines. And then here are the postulates, which are specifically about geometry. And these are the 5 postulates. There's not 22, there's 5. One might think a little bit about why that's different. And now, sort of get together a little bit and move around and talk things like about what's the distinction between the 2 groups of Euclid's postulates? What's the difference between the postulates and the notions? What do they each mean by line? And can you think about, and you may very well have other distinctions here that you want to bring up. Great. So let's take a few minutes and chat about it. Maybe someone brings together here so you can have an extra talk. Lean forward to the one behind. I'm not trying to.
Think about the questions.
Yeah.
But we need to try to give out one answer.
Well, no, I mean, we don't think it's not, it's more what, what.
But the fourth question, one amazing important from what really distinguishes between the two first Hilbert's axioms.
Oh, yeah.
I believe that maybe we have some more smart form of axiomatization, formalization of language. But that is more intuition.
Yeah, certainly in the definitions.
Kind of definition. But everybody here will give one answer to each question.
Well, yeah, right. I mean, we're not going to spend.
I'm not a logicist. I'm an astronomer. Okay?
An astronomer. Oh, all right.
I came here to understand a little bit about the logical meaning of space.
Okay.
Well, kind of call it like a formal space. People say logical space. I believe that you work with the structures.
That will show up. But I mean, there's, yeah. Good.
This is it.
Yeah. No. I'll go ahead with yourself. We'll make it in English. Yeah. Okay. Yeah. You know, I think that you're saying something that is relevant enough. So why don't you say this to everyone?
All right. Well, what I was saying here is that an important distinction between the definitions in Euclid and Hilbert is that each concept in Euclid is defined by its own. So you have a definition for what the point is, for what the line is, and so on and so forth, and they are supposed to stand out for themselves, in a sense. While in Hilbert, definition is done completely implicit, which means they only make sense as a whole, as the whole theory. So it when you have the whole theory, it should be specific enough to give the meaning of the individual terms. So it's holistic, and the other one is not. That's all.
So that's a good point. I mean, it's that, right? So there, in Hilbert, are there any definitions in Hilbert? Maybe none yet. Right? I mean, well, there's the implicit definition of the whole thing. Oh, yeah. There's the implicit definition of the whole thing. Do we? I don't know what I had here. Well, look more at Euclid for a second. What's the distinction? Can you see what I was trying to say? Why do I have these separated? The first four from the last three. Why do I have the first four and the second three as being two? Is what built on the first one? Is there anything more and a little different about this? Yeah, I mean, I call this an indicative definition. It's trying to give you a feeling for it. Right. While the last ones are more what we might call a stipulative definition, and that's what Hilbert's actual definitions. I should have had one, something like, well, Hilbert has probably pretty much the same definition of a right angle. But you have this distinction that's well known, right, between the stipulative definition as being an important part of mathematics. I think this is tending towards what we are thinking of now, and I'm not nearly enough of a historian to know how much this differs from the rest of Greek, or let alone what was going on in Babylonia or China in the 3rd century BC. Yeah. So now what about the distinction between the postulates and the common notions? So those are the postulates, and these are the common notions. Yeah. Well, but is item 4 construction?
Huh?
Is item 4 construction?
Item 4 of postulates?
Postulate 4.
Oh, yeah. At all right angles equal. Yeah. No, this one is not.
So historically, postulate 4 and 5 is being added later.
So it's a.
There is a difference between there is a difference between postulate 1 and 3 and 4 and 5, exactly, because it's been added later historically. But I mean, what he's saying, I mean, if you look at the Greek, you can see the postulates are imperatives, at least the first 3, while the common notions are indicative or whatever it's.
Maybe I'm ignorant. When you say added later, you mean by commentators on Euclid, or is that?
Yeah, I don't know. I'm not an historian, but I mean, it's the first version. Yes, probably by commentator or later. I mean, edition of Euclid's postulate, and that's why I mean, postulate 5 clearly is different from the other ones, and everybody always had this feeling. And
well, I think that's true, but I'm not sure that it's. It's added later, maybe in the sense that this is what Euclid did that was not in the literature before him.
Yeah. But still, I just wanted to stress that there's a clear difference in what postulates ask the reader to do and what common notion asks the reader to do, and that's exactly in respect to.
Okay, no, right. That's certainly right. That the first 3 are constructions, and
there's also another important difference between postulates and common notion, which is the scope.
Yes, go ahead.
Yeah, I mean, common notions can be applied to almost anything that can be object of our mind, like postulates are specific to geometry.
Right.
And that's why these are what we call axioms in modern times.
Exactly.
It was important to distinguish between the common notions or fundamental concepts and the axioms and the third part, that is the postulates. Postulates to Carnap, for example, is not knowledge. It's a kind of convention that you put in the end of the system. But axioms to him was knowledge, a priori knowledge. So we can start, for example, one topological space with axioms, And when you put the postulates, metrical postulates, you construct some kind of metrical space. It's one difference.
Oh, okay, thank you. Yeah, keep that there and pass that around between. All right, so what's the difference, and I'm not sure if it's evident in what I've written here, but maybe people know, between what Euclid means by line and what Hilbert means by line. And here I think that there's a really clear, specific difference. What is it? People were nodding, so I thought I was going to get an immediate answer.
I'm not sure if it is about a difference of meaning, but in a way it's more like a difference in how they achieve it. You know, like Hilbert is, maybe there is some sense in which Hilbert is uninterpreted, so line may mean a chair or not,
Yeah.
but I don't think it's in his intentions at
Well,
all.
I disagree, so let's see if anybody else does. Yeah.
Maybe for Euclid, the notion of infinite lines, some approach the notions of infinite, and Hilbert is not it's not worried about that indirectly. It's, I don't know.
Yeah. No, I mean, I think actually that if you look, that maybe we can go back, that Euclid really, lines are line segments. When he says line, our reading would be line segment. It has, the ends are points.
But and this a line is a breadth length.
It's a breadthless length, but the ends of a line are points. So every line has ends.
It's a segment. Okay.
And this, of course, means that even though, but of course they can be infinitely extended. We'll see that postulate in a minute, or not. But in fact, I guess that is in the postulate, right? Postulate 3, you can move it, extend it. You can extend it arbitrarily. But my understanding is that Euclid, like Aristotle, who's very clear that there is no completed infinite, and so so that's the difference that I'm looking at between Euclid and Hilbert, because Hilbert clearly is. Okay, I think we pretty much. Yeah, well, yes, okay, that was what I wanted to say. Okay, so now I'm going to go back and talk a little bit about the general setting of what I want to do in this series. And as I said, this sort of combines two rather distinct things that I've been doing in the last 10 or 15 years. One is talking about geometry, primarily from the standpoint of math education. And there's a new textbook, a textbook for the people who are teaching the college course in geometry. Three volumes just coming out, and I wrote one on axiomatics along with Andreas. And so that line of thought was in one side, and in the other, I got into this work with Constantine about categoricity, but it ended up, as I'm going to say in just a few minutes, being worried about what concepts are, and so those two merge in these lectures. So I want to first start by just being pretty precise about what I mean by logics. And a really crucial point from, I think this is, in one sense, the most important notion in model theory. A vocabulary. We fix a language to start with. And much of the philosophical discussion is marred by the fact that, well, we all know Dedekind. And in second-order logic, vocabulary is meaningless. And so people start talking about things and are doing that absent-mindedly. And so a vocabulary is a collection of relation and function symbols. A constant is a zero-area function. And if you have a set M, then you can construct a model on it by determining the interpretation of each of these notions. This is just basic model theory. And these definitions, why I'm saying it's become relevant later, but this is the definition that's given in 1.2, maybe page 4 or 5 of Button and Walsh. And now semantics, this also is a long story that we aren't going to go through, but whether we're worried about or Robinson's version or somebody else, there are fine differences that I don't think need to be important. So it's just that to define whether a formula is true in a particular structure, the first thing you do is add names for the elements of that structure. Now, when I said the thing with Tarski has a function from giving a valuation to the variables. And there are subtle differences there, but I don't think they're relevant for what we're doing. And then that gives you an atomic a truth value for each atomic formula. And then you work by induction, saying that there exists x phi of a bar x is true if you have a constant that makes it true. Yeah, and you've already defined the formulas of lower level, so you know that. And so this is the Tarski-Robinson definition of truth. Where did I set the thing down? All right, and now on the syntactical side, we have certain logical operators, propositional connectives, and or not, first-order quantifiers. We may sometime, part of the time, talk about more things, but basically that. And you define L of tau formulas by induction. And an L of tau theory is a consistent set of sentences, and this word pseudo-elementary will show up somewhere, where if you build a collection if you have a theory in a language tau prime extending tau, and you think about the redux, forget about those extra things, then that's called a pseudo-elementary class in the smaller language. Okay. Right. Now we get into some of the more philosophical issues. Button and Walsh introduced a notion of modelism as an attitude towards model theory, with this claim as to how structure should be explicated. Now, we've actually given the formal definition of structure as they did. The Modelist Manifesto. Mathematicians frequently engage in structure talk, and model theory provides precise tools for explicating the notion of structure they invoke. Specifically, mathematical structure should be understood in terms of isomorphism in the model theorist sense. Okay, great. That's fine and particularly because his definitions are exactly what I would do, or pick up Marker's book or any other model theory book, and it'll be the same. But then it's surprising to say, how can we pick out particular isomorphism types? Is this a problem? So now, just clarifying their argument a little bit. They talk about blunt objects modelist, which is that a model is an abstract object, pretty much a Platonic view. And then a moderate or concepts model maintains that the talk is, no, it's not about Plato's heaven. It's about these concepts roughly in the sense I've described. I mean, yeah, okay. And then they argue, I mean, it's page 146, but at least half of the previous pages are developing this argument, that any kind of modellist fails to explain either how we return to bona fide refer to bona fide objects, or how we acquire and use concepts that are as fine-grained as isomorphism types. Okay. Now, what struck me, this just seemed like a crazy question. That is, how do you identify an isomorphism? You said of a structure. So I've got this structure here. I'm a mathematician. I've got this structure here because I just built it. I just worked in naive set theory and wrote down the structure of an omega sequence. And what is the isomorphism type? It's anything that's isomorphic to what I just gave you. Now, I think the reason that this is a problem, and here's what Carnap that we have to understand where the question is being asked. And so we've worked out 4 notions of frameworks. The pre-theoretic or structure framework is informal, natural language. Consider intuitive pre-theoretic mathematical concepts. There's somebody, I can't remember if it was Rodrigo or one of the other people I was talking this morning. What are the natural numbers? 1, 2, 3, 4. And you can sort of think about addition and not so well about multiplication. And then the second framework we call the informal or formalizable. And this is what mathematicians do. They, if some of them, if press would say, okay, I could formalize this in ZFC, or you're a set theorist, I could formalize this in set theory with 7 accessible cardinals. There's this basic kind of notion that you aren't paying particular attention to. You're just doing mathematics. And then there's formalized, which is now you have to be a logician, because it's a mathematician who has written down the words that I described above, the notion of conception. And even then, when we ask the kinds of questions we're asking today, the logicians don't have to do that. It's philosophers and the logician thinking about what he's doing that raises the kinds of questions like, how do you pick out an isomorphism? But when you've asked that question, then I think I've just said this. If there's any question, we can go back. This is what mathematicians do. Yeah, so now this is how I think Button and Walsh would answer me, or answer the. We weren't asking the mathematician. We were asking the modelist, who with that level, they actually know what logic is, and so they need to give you an explanation in terms of the description in the logic. And in that case, you are asking for categoricity, that in a certain logic there is a unique model of this structure. So this is not reference by description. Description is the category. And I guess our point now is that they want to claim that you can't. Second order logic, the answer to this is somehow involving higher order concepts. Not bad. And there is no weak. I think that's at some point. Yeah. Oh, sorry. Thank you. At some point, there's a list of on just a couple of pages. Here are 8 logics that are weaker than second order, and none of them work because either they don't actually work or they involve concepts that mean you're going in a circle. And when we get to the paper with Constantine, I'll give some arguments for why our logic is not circular. Most important being, it's about arbitrary theories. We aren't assuming anything about arithmetic because the arithmetical notions have nothing to do with our logical rule. So let's say a little bit more about what we call framework concepts modelism. So they give a distinction between objects modelism, which is really you're only talking about structures, and concepts, which they give very short shrift to this. Concepts are a can of worms. It's just too hard. We don't. How do you even give objects? You can identify relations. You can say something is yellow because it's a different wavelength, but concepts are just beyond. And basically they spend maybe a page on this and then just say we aren't. It's just not something we're going to talk about. On the other hand, we think it is something you can talk about. And one step in talking about it is those frameworks. And the other is to lay out in more detail what the frameworks are about. And our work was built on a paper by De Benedetto and Rossi, which is it's now appeared in Philosophia Mathematica, and a lot of their explanation is of the first stage, and the work of psychologists and neuro whatevers in the last couple of decades, with doing detailed studies of how animals and children pick up notions. And our notion differs from that in the sense that that's a pretty good notion of how you do things at this first framework. But the later ones, mathematics has been developing as I started only 2,300 years ago instead of 40,000 or whatever it is that I should have, if I knew any prehistoric history. And Framework 2 provides more careful analysis, more precise descriptions of the informal notions, usually in some sort of naive set theory. And naive set theory here for, maybe most of you are too young, but Ramos is, I think he coined the word, or no, maybe Mistovsky coined the word. But at any rate, Ramos writes this book in the 50s that explains in a very actually pretty clear, but very imprecise from a logician's standpoint, the development of mathematics and of set theory. And Framework 3, now we have the logical structures, and we have the kind of distinction that was actually being made by Button and Walsh, and so this is where the question makes sense. And in some sense, we're going to be trying to describe how it does get an answer there. And then Framework 4s. Now, where are Euclid and Hilbert in these frameworks? And are they in the same place? What do you think about that? Non-rhetorical question because I have to answer on the board, sorry. But they aren't, either one of them, dealing in formal language. Hilbert is writing in German and Euclid in Greek. And we're going to try to understand the difference between them working from the level of Framework 3. But they're basically in this same level of Framework 2. Just different formulations. Okay, and now we're going to move to Euclid. If anybody needs this now or later when you go home, Euclid's, if you Google Euclid's elements, you get you get many things, but you want to get something by at Clark University. I keep calling the guy Clark, and Clark is not Clark's the university, not the man's name. It'll come to me in a minute, but it's an annotated version of Euclid's Elements, very nicely presented. It's really I mean, you could have the book, but this is, and it's actually easier to move through than the book. One of very rare, something I very rarely say about things on the computer. Okay. So this is the framework I'm going to use, which is not Euclid, and not exactly Hilbert, depending on various times. Whether this is all going to be consistent, I'm not sure. So if I'm Hilbert, I have a two-sorted universe, points and lines. There's a binary relation that says the point A is incident to the line L. There's a ternary relation that says A, B, and C are on the same line. And a quaternary relation that says two line segments are congruent. And a sixthary relation that says two triangles, the angles are congruent, respectively, and the line segments are. Yeah, sure. Well, I mean, this is, I think that it's pretty clear from what his axiom of determination is, and in fact, I'm going to have that on a slide in a minute or two, if I remember. But, well, yeah. Oh, yes, this is what I'm going to say. There are notions here about whether it's one or two sorted. That isn't really a big deal if it's points and lines. And Tarski does it with one sort, and I'm going to slip into doing that a little bit later, but that was not a big deal. Whether you have a difference between congruence and distance is absolutely a central distinction. And how you compare area is an even bigger in the sense that it's harder to work out what it actually means. And when I wrote that 4 there, it's because Hilbert and particularly as expounded by Hartshorne, solve the third problem, but they do it by slipping in relations of arbitrariety. And they never mention it because they're mathematicians. So here's how, so this is exactly the axioms that we mentioned before. And I've just written them down in formal logic, or I've written one of them down in the formal logic I just saw. And so line segments would be given by pairs of points, and for area AB there's a C such that, yeah. All right, and now you have to have a congruence postulate. This is something that it's well known there are difficulties with what Euclid did that I'm not going to spend much time on here. I'll mention a little bit about it. But Euclid is just, the statement is SAS, at least that's what we call it in American books, side angle side. If two sides are if two sides are congruent and the angle is congruent, then all of them, you have all of them. And so congruence of triangles means the pairwise, I guess I wrote that before, right? Okay. And I'm not quite sure why it says replace it with a single axiom, but yeah, and what I said here, this isn't an axiom, it's a proposition in Euclid, but you know, even if you look at what's his name, the edition from the 20s. I don't remember. I'm blanking on the translator, but I'm surprised nobody's told me. Keith, yes, that's what I mean. Thank you. This notion of superposition just sort of slips in, and there's worries there. And we'll say something. And Hilbert writes it as this axiom doesn't have, if you think of this as an axiom, it's not a problem, but that's the point, that it was supposed to be a theorem, and it's only a theorem if you have somehow justified this use of superposition, which he hasn't. Okay, so, and then Hilbert has betweenness, just asking about betweenness, which tells you that they are that it's a linear order, a dense linear order. One congruence postulate. Now, I've said SSS here because this slide came from some stuff that Andreas and I worked out, and we thought it was sort of neater to have SSS be the base one. It seemed to be cheaper. And then the parallel postulate. Now, the question is, what are we going to do? Where does distance come from? And the crucial distinction of Hilbert is showing, defining the field, and then, well, I say Hilbert, it's actually Descartes, but Hilbert making it precise, that you have a field of line segments, which is just a line, the numbers are the equivalence classes of segments of the same length. And Hilbert, the Hilbert book just doesn't mention circles. There's no development of circles. I won't say the word doesn't occur somewhere. And Hartshorne notices that if you add an axiom that of circle intersection, that two circles that are small, close enough together, the centers are close enough together so they can intersect, then they intersect in exactly 2 points. And by adding that axiom, you get some you get the field that develops becomes Euclidean rather than Pythagorean. There's some details there that are interesting. Now, the goal of book 1 of Euclid is to prove the Pythagorean theorem without using a measure of length. And I say that this is the goal. I'm relying a lot on Ian Mueller's book about the history of the geometry, but it's essentially that that the Pythagorean crisis is being thought about, and you don't want to worry about exactly how you handle your rational numbers. I mean, there are approaches to it. I mean, Eudoxus and in Euclid, you get ways to deal with your rationals. You know they're there, but they're funny enough that they aren't as serious as points, right? Yeah. And so so these are the two propositions that are going to keep showing up in this talk. Well, the Pythagorean, not so much. That's 48. But, here was my question. Right. So book 1, proposition 35. Parallelograms which are on the same base and in the same parallels equals one another. If in a triangle the square on one of the sides equals the sum of the squares on the remaining two sides of the square, then the angle contained by the remaining two sides of the triangles is right. What does equal mean? What is equal a property of? Well, parallelograms which are on the same base and in the same parallels are equal to one another. Yeah. It's area in some sense or the other, right? And also in the second one, right? Because the sum of the squares that you add up those areas and you get the same as the area of the square on the hypothesis. Okay? And it's phrased this way deliberately so you don't have to worry about whether these side lengths are irrational or not. And this is someone who knows more about the history than I do has argued this. So now, what about these? What do you think? What do you think? Oh, sorry. Yeah. Thanks. Yeah. Thank you very much. Anybody that points that out to me, I appreciate it. What is the notion of area? Maybe you can think a little bit about this, or go ahead. Yeah. Is it? Yeah.
I like very much. He does an analogy with covering a field with grains. Like if you want to plantation semear. I don't know how to say that in English. Seed. Yeah. If you want to seed a field, so he explains the principles of the axioms of area with that analogy. Like if you have the same size of fields, you need the same quantity of grains to seed it, and if you divide a whole space in shorter, in not disjoint in disjoint places, the sum of the grains that you need to the sum of the grains in each space is equal the total space, and if you have two equals one, this and the third one is every field needs to have at least one grain. Like if you have any space, you need at least one grain. Mm-hmm. So like with this, he introduces the three axioms of area. I find it very nice analogy. But it finds axiomatic. It finds axiomatic area with these properties of.
Okay, right, and I think that'll be something like. Probably comes up in the last lecture, or a later lecture anyway. But how do you tell two objects have the same area? How would your high school students, or how would a carpenter looking at, or somebody measuring a
and putting them over each other? Overlap them.
Okay, so without overlapping, cut it up and move one over to the other.
Exactly, and I think it's like this that Euclid makes the proof, right?
It's one step in the proof. You'll see that that's a very interesting subtlety. But if you're a modern carpenter, how are you going to do it? Carpenter or carpet layer. Say somebody's selling carpets. How do they talk about whether if somebody who is selling carpets, rugs, how do they describe the area of their? Yeah, go ahead.
They send by the square meter, so it's decomposed in squares.
They can decompose it in squares, but how do they actually do it? Don't they get out a tape measure?
One initial square, like for comparison.
Well, I don't think they do that. Well, no, that's how they sell it. I mean, that's how, I mean, we're using sell in a different word. There's a it's a different meaning of sell. You're saying how do they convince people to buy it, and they show them the pretty picture, the pretty piece. I'm saying what is the way in which they measure the amount of the sale? Do they really sell by weight? It's a way it could be done. That's right. But what is the way that they actually do it? Yeah, the measure. Yeah, they measure it. They measure the height and the length and the width, and multiply and tell you how many square meters, right? And these are two quite different ideas. Euclid is deliberately not using the second, although there's no doubt that the carpet people were doing that in the Forum in Athens at that point. But the connection between them is one of the big issues that we're going to be talking about in this series. Right, and here's actually the answer to the question about, is it just decomposition? So I'm going to sketch this proof probably several times, but parallelograms which are on the same base and in the same parallels are equal to one another. So we want to claim that this parallelogram ABCDE and EBCF have the same size. And how do we do that? Well, they're both sitting in this big figure, the AFBC. And if I take this triangle away, I get this parallelogram. And if I take this triangle away, I get this parallelogram. But these two parallelograms, the two triangles that I subtracted, are congruent. So by equals minus equals are equal, I have the proof. Now that's different than decomposition because because I use subtraction in particular. And that's necessary. If you only use decomposition, this fails in non-Archimedean fields. And now, here's the proof of Pythagoras. And I'm not going to go through it in any sort of detail, but it actually is by decomposition. And by showing that somehow that half of this triangle is given by one coming up here, and it takes a long time for him to work this out, but you get a decomposition of the sum of the sum of the squares into it and the base. And I'm pretty sure he uses decomposition. It wouldn't harm the argument if I remember it that long. but it definitely has nothing to do with distance. It's done in terms of this being able to shift polygons around. Now this worked for 2,000 years, but in the 19th century, two issues arose. One is, why does the common notion the sum is the part is smaller than the whole hold for areas? See, this is easy for lengths because you can just see the length being sit inside it. But I get two figures where, because the one of them's skinny and the other one's more compact, I can't put either one inside the other. And even if I could, the central issue even turns down to, suppose I have two squares and one has bigger area than the other. Does that imply, I'm sorry, yes, has bigger area than the other. Does that imply that the second one has a smaller side length? And that is needs to be well, you get this out of Hilbert's theory of area, but you don't get it out of any theorem of just handling equal decomposability. So again, this will be sort of, this is one of the other lectures, but this is a problem that Hartshorne raised of, can you prove the common notion 5 for area without using some kind of measure of area? And as far as I know, that's actually an open question, which is not exactly mathematical, because what does can you prove mean in that sentence? In what framework are you asking that? What I mean by prove? Okay, so now I want to point out that even when we have a pretty good formal notion of what things mean, or well, at least an informal notion in the level 2, do we really have the same concept? And van der Waerden writes, so he's looking at Euclid Book 2. Yeah, I should have had something up, but it talks about rearranging triangles, and as I'll say in a minute, the goal at the end is to prove that any polygon has equal area with a square. And then, since squares are obviously comparable, we've given them. But that isn't what Euclid says. We studied the working, not Euclid, what van der Waerden says. We studied the wording of the theorems and tried to reconstruct the original ideas of the authors. We found it evident that these theorems did not arise out of geometrical problems. We were not able to find any interesting geometrical problems that would give rise to theorems like 12.4. On the other hand, we found the explanation of these theorems as arising from algebra worked quite well. Therefore, we adapted the latter interpretation. So he and Vey both wrote strident articles like this. That is, Proposition 7 in Book 2 says, if a straight line is cut at random, then the sum of the square on the whole and that on one of the segments equals twice the rectangle contained by the whole and the said segment plus the square on the remaining segment, as squaring a binomial. Yeah, it's not surprising that van der Waerden can read it that way. It has nothing to do with what Euclid was talking about. There's no norma. And it's not a question of whether it's formalized or not. It's a question about what the real notion is. Are you talking about areas or are you talking about lengths? And here's, we got some of this other, so
Arpad Sabo and Piotr Placek. Book 2 constructs from an arbitrary polynomial a square that has the same shape, same area, without any use of proportion, but just by the rearrangement of polygons. This provides a method for comparing the areas of polygons with a single parameter, the side of the resulting square. Now, there's 2 points about this. When I say rearrangement of polygons here, that suggests decomposition. And Euclid is not using decomposition, he's using the subtraction. And I don't think these people made a mistake, they just were using the word loosely. And the second thing is kind of a complaint with Button and Walsh. They say we want to worry about structures. If we're going to worry about structures and what's going on in them, we need relations. And relations are concepts, they aren't structures. And that's why a full theory of this stuff is going to have to involve the analysis of concepts. Okay, now I'm going to say something. This I wrote last night because I've been struggling with things that will show up later on, but here it's true already. Suppose I want to construct a parallelogram equal to a given triangle in a given rectangular angle. So let's see, we brought this chalk, didn't we? Somebody showed me chalk. Oh, okay, right. Oh, it was the wrong size of box. All right. This is, I'm kind of out of order here. Hartshorne eventually takes the notion of a figure as being any disjoint union of triangles. And this argument works just as well for that. But so I have a figure which is some collection of triangles like that. And I want to first assume proposition 1.42 that says if I can do that, it says for any particular triangle, I can go over and you give me some angle. Then I can find a parallelogram with that angle. Yeah, parallelogram with my sloppy writing that has the same area. And that proof is in 1.42. It's not really an issue. But now suppose I just have this thing that's a disjoint union of triangles. How do I make it into a parallelogram? Well, I pick one of them and I do this. When I do this, the first time, it's arbitrary. I don't care what happens to this angle. But now when I built that parallelogram, I have this angle that I want to preserve. And so when I take the second one, I do that construction again, but I do it in this angle. And for the third one, and so on. And in the end, I get a parallelogram that has the same area as this original figure. And then proposition 1.14 is a similar kind of thing, showing that you can turn that into a square. And then Euclid says I'm done because he's using the common notion 5. And it turns out that that's quite tricky. And a man named Dassault introduced just an axiom that says that. And I will talk about that in a later talk. But that's really a very subtle issue. Set it down. Oh, we are getting close. Okay. Now, the part of the point I wanted to make here is that in book 2, these constructions are concrete in the sense that it says, given this object, turn it into another one. The difficulty comes when you say, if you have some sort of abstract decomposition or equal complementation, how do you know something about the result? I guess I'll say this later, but the statement that you have an equal decomposition is an L omega 1 omega sentence disjunction. Like you say, it's this, you can do it this way, or this way. And if I want to apply that, I say pick one. But if I want to look at the negation, then I have to know about each one. And that's a problem. Okay, now I guess I'll begin the representation. And this is 4 years history of the calculus, I guess. It's sometimes said that Descartes arithmetized geometry, but this is not strictly correct, because for almost 200 years after he said the coordinates were essentially geometric. That is, the objects of the field are line segments. And picking them out as being abstract numbers is something that happens, as he says, in the early 19th century is when it begins to be happening. Oh yeah, okay, and so this is actually, we can probably get through Bolzano. So Bolzano, in this period, right, he's in the early 19th century, discusses the dissimilar objects found in Euclid and finds Euclid's approach fundamentally flawed. His general position is that one must analyze conceptually prior notions, like line, before more complex lines. So you have to know about the line before you can talk about the plane, because planes are made of lines. In particular, he objects to Euclid's proof in Book 6 that similar triangles have proportionate sides. Firstly, triangles that are already accompanied by circles that intersect in certain points, then angles, adjacent and vertically opposite angles, then the equality of triangles, and only much later their similarity, which, however, is derived by an atrocious detour from the consideration of parallel lines and even of the area of triangles. I call this Bolzano's challenge. There's two aspects: the evil of using two-dimensional concepts to understand the line, and the atrocious detour to reach similarity. And I guess the next slide's right. Yeah, let's stick with this. It'll come, side split will show up in a minute. So in Euclid 1.37, Euclid shows the area of a rectangle determined by its base and height. In 6.1, using the theory of proportions, and then there's a hidden use of Archimedes. Of course, it's hidden partly because we're still a generation or so before Archimedes. He determines the area of a triangle or parallelogram. The role of proportion is to show that the area of two parallelograms whose respective bases, well, it's in 135. No, it's not there. It has proportionate areas, which are then proportionate to the base, even if the bases are incommensurable. Now, I'm going to go through this later. I'm just trying to give a general picture here. And then from that, you can deduce that similar triangles have proportional sides. Now, all of this, I'm throwing around the word proportion. And yeah, so this is a good idea, a good place to stop. So he did this because he knew there were irrationals around that didn't really know quite how to deal with them. And this is, I mean, Eudoxus has an approach, and you can, and Archimedes uses it in a very careful way, but this was not so careful, and his theory of proportion considers proportion as equality of ratios, but numbers are not magnitudes. So the kind of modern thing of saying, oh, we'll switch over, we'll just work with numbers, is just foreign. That's not involved. Okay, so we will start with magnitude and ratio next time. or comments? Any thoughts?
Questions, comments?
Yeah, could you explain again how L omega 1 omega enters the picture of that? It is about the arities
Yeah.
that
Yeah.
of the relation of, the
Okay,
relation
I'll-
of equality.
Okay, so let me say it quickly, and I'll do it in detail. But the point is, you have an equal decomposition of two figures, but you want to prove this is transitive. So you also have one that comes from here. When you try to prove the transitivity, and this is laid out in Hartshorne, you have to refine the decompositions. So before you had two things that had n triangles, and now you've got some duad, some maybe the picture is better. I break this guy up like this, and this guy up like this, and then I have to kind of take the intersections as they move over. And so I get something like this in order to get the transitivity. I've done that very badly, but I think the notion is there. And so if I try to write this down, I say two figures out of n equal complementable, if you can do it with n prime. Now I've got a first order n area relation, or maybe three n areas, we haven't tried to fix the plan. But in order to get the whole notion of these two are equally decomposable, it means equally decomposable in m steps for some m. But the abstract notion doesn't know what m. And so you do the at least there may be a way around it. There is a way around it if you assume if you use Hilbert's notion of area. And that's what Hilbert does, and it's what Hartshorne does in explaining this. But the question of whether you can do it without area is an open question.
Now I would like to discuss more the first part of your talk about concepts, right? The shared notions, right? And I think that we will overlap on this, and we have already discussed some of this stuff, but I have told you this argument that we have in philosophy against the the mental view of the concepts, that's or mathematical concepts, because basically if they are part of the shared structure that we have somehow be in contact with, they cannot be mental, because or they cannot be inner. I don't know if mental for you is inner or external, in the sense of how a concept could be shared and inner and mental. So we have this famous Kant's argument that time is shared, for example, because for us to have the experience of self-consciousness, we must have our inner states ordered in time. And so time cannot be one of those inner states because, well, the ordering of the states cannot be a point of the ordering. And so it is not a mental state in this sense, but it is a shared notion that we happen to be in contact with, but it is not inner. So do you distinguish between mental states and inner states, or
okay, so I'd have two responses to this. One is about what inner means, in the sense that as we have this conversation, you're explaining to me something of Kant that I didn't know before, and so it's changing my state. And so inner does not mean obtained only by reflection. I mean, at least, maybe inward does, but holding a concept or getting a concept does not mean only something learned by conception. It by reflection. It involves interactions. And the second is, order seems to have somehow magically become linear order. And I would certainly think that the ordering of mental states is not linear. And so you can recognize that certain states are organizing the ones below. And in fact, this the authors that I got from the very beginning, from the Stanford Encyclopedia, are very clear about there being an ordered, that essential of this to this mental states version is structure on the states, and that's a key part of the philosophy of the theory.
Yeah, I think that's the first answer that you gave is closer to what I think, but that is we have a conversation that means that we share some common ground. Yes. The communication presupposes that we have something in common to communicate, and this commonality of the concepts cannot be internal in the sense of being private. If it's private, it's not common. So
yeah, well, I mean, this notion of privacy seems wrong to me. I mean, the concepts are things that are possible to be shared. That's it. Yeah. So when I said they were individual to begin with, maybe I should be more careful about that. Each individual can have a particular, a really fine-grained thing, but when we talk about concepts, we are always talking about things that people, that various people have. This is a word, and we have some meaning for it, which may or may not be exactly the same, but that's the kind of thing that I'm thinking about.
Yeah, I agree completely with you.
It's a very good point as far as sharpening what I said.
I only object to the mental nature of concepts. We can discuss more about this.
Yeah, I have to understand what the alternative to mental is.
Yeah, that is the hard part. Yeah, I think.
Jargon in I think in philosophy of logic, especially in Freire, is like this fight against psychologism. Yeah. So it's like a fight against putting concepts in these psychological terms as Stuart Mill has done before. So he was like trying to fight against this, and the argument is going in this direction of like saying it cannot be, it has to be fundamentally shared, and therefore it cannot be purely mental. It has to have some objectivity that goes beyond what is purely in the mind of the thinker.
But Freire also uses the word thought, which it needs not be mental.
Yes, he talks about thought, but thought for him is not mental.
Oh, thought is not mental. Well, there we have a problem.
I mean, in a sense, what he does is that there are two dimensions of what we in our daily usage of the word thought we mean. It's like saying, for instance, when I think of an elephant, I have something in mind. I have a picture or something like this, but the thought content of it is not what I have in mind or the picture or so. Is exactly what we understand commonly about it. This is the propositional content is exactly not what is in my mind about it. You know, something. So it goes in this two-dimensional stuff.
Yeah. So this is intriguing. I mean, it might be that when I made this part thing of the name and the content, that the name is certainly mental, I think, in the sense that we're thinking about, while the content, I mean, I'm not sure. I mean, it still seems to me like the content is what I'm thinking it is, which is different than what you're thinking it is. But then whether there's, you know, I'm trying to pretend that there is one concept of line when I really know that it keeps changing. So
basically what I'm saying is that maybe you are completely fine and right. It's just that some people reading this might cringe at the, like, say, mental. Yeah. Mental is not shared.
Yeah,
you know, like
thank you. I mean, we've actually, maybe I'm not addressing it well enough yet, but that has actually arisen in discussions. So
what I'm saying is, you're probably thinking it right. That's what I'm saying. But,
I see,
but the word might bring memories to people versed in history of.
Very good. That's very helpful.
Okay. Well, some questions? More. So, thank you, Professor Baldwin. Bye. So thank you, Professor Rodrigo Freire from IME to accept to give this mini course in Foundations of Mathematics, and the title is On Mathematical Defining. Thank you very much, Rodrigo, to be here again in IME-USP.
Thank you, Hugo, for organizing this. And well, the mini course will be about the topic of definitions in mathematics as a whole, and it is an unusual topic, right? In general, mathematicians are very much concerned on theorems, and mathematical courses usually are directed towards specific theorems, or in logic we have the discussion of theorems in general, but we usually don't have much discussions about definitions and what can count as a definition in mathematics. So this is the point of this talk, this mini course. So I have here a plan of the mini course. I will try to give a general picture of the whole in this first meeting, and we shall discuss the first 3 or 4 or maybe 5 of these items in the first meeting, and then I will try to give more or less precise view of first order definability, which is the subject of this there's 3 topics. There's 11 lemmas in definability theory, Robinson's joint consistence theorem, and Beth's definability theorem. These 3 subjects are strongly based on the back and forth approach. There are other approaches to this, but I chose the back and forth approach because it is useful for other results also that we will mention. And then I will try to give a flavor of omega logic definability, what I'm calling omega logic definability theory. I will not be able to give proofs, detailed proofs for the results here, but I will try to give a sense of the techniques involved. Back and forth is not going to work here. Our approach is based on the canonical model construction and some refinements of this method, the method of consistencies families and Hintica sets. So Freire is our hero here in the first order definability theory, and we have Henkin here, Henkin, Hintica, and others in this second part, right? This is the technical mathematical content of the mini course. This the first 5 topics are more conceptual, although some technical issues will also arise here. So we begin with a problem. The problem is that defining is one of the 2 fundamental types of mathematical practices, the other one being constituted by the practice of proofs. So mathematics is here conceived, since this course is a course in the foundations of mathematics, it is important to give our view of mathematics. And mathematics is here conceived as a pair of practices. We will discuss this in more detail, but mathematics is viewed as the practice of proofs and the practice of definitions, right? And these are, in my conception, 2 fundamental or fundamentally different kinds of practices. It is, in my conception, not possible to reduce one of these dimensions of mathematics to the other. You cannot reduce definitions or the practice of definitions to the practice of proofs, right? The fundamental difference can be explained in the following terms. Defining is an interpretative practice. Defining is a semantic dimension of mathematics. It is to, roughly speaking, to choose an interpretation, to identify an interpretation of a predicate. Proving is a symbolic practice, right? To prove a proposition is to construct an appropriate sequence, chain of propositions leading to the last one, the conclusion that is being proved. Of course, there are many other background issues behind this, but we should start at some point, because then I will explain other background issues as we go on the way. For example, we view mathematics, of course, as a theoretical activity here. So there is a fundamental tension in the foundations of mathematics, or in the history of the philosophy of mathematics, of whether mathematics is more art, a kind of art, or more sort of science, right? Mathematics is art, or is it science? There is a deep issue at stake here. If mathematics is more something that it is intuitive. It is something more akin to perception than to understanding. So that's the issue, right? If language has something to do with mathematics, for example, right? This is not in any way a trivial question, right? In the 20th century, we have seen the victory of the theoretical view of mathematics. Mathematics is something like a theory which is axiomatized in some language, and which language we choose to do mathematics makes a big difference, and so on. But this is not uncontroversial, right? We have in the philosophy of mathematics this intuitionistic school that thinks that mathematics is more intuitive, that language is something posterior, and well, this is very much theoretical, but it is important to give in advance that we have a series of presuppositions, right? And we shall try to understand these presuppositions as we go along. So why definitions are important, right? Independently of conceiving them as interpretative or symbolic, definitions are very important to mathematics for more than one reason. For one thing, definitions are usually starting points for proofs, right? I suppose that an axiom, for example, does not count as a proof. When you give axioms, you are not proving something, right? But are you defining something? In which sense? When we axiomatize a mathematical subject, in which sense we are giving a definition, right? This is an important question. Well, if it's not a proof, if an axiomatization of a theory, you give some axioms, for example, the axiomatization of arithmetic, it's not a proof. So it must be a definition if mathematics has only definitions and proofs. What kind of definition is this? In general, the directions of inquiry pursued by the mathematical community. Ulisses vai jogar fora. So the directions of inquiry pursued by the mathematical community, the notions mathematicians care about, the mathematical subjects, they are given not because by proofs, but by definitions, right? For example, in mathematics we study fields or rings or groups or manifolds or topological spaces or measures or stuff like that, and operators, and these are given by definitions, not by proofs. So the mathematical subjects are given by definitions. So this is very important, right? In spite of these, right, mathematical definitions are not well understood as mathematical proof. If you ask a mathematician what is a mathematical proof, I think that he can more or less explain what it is. there's a sequence of steps following certain rules that eventually came to a conclusion. Some logical rules in a chain of claims, making a chain of claims. But if you ask, what is a definition? It is unlikely to have a reasonable answer. What is a definition? So these are not as well understood as mathematical proofs, and we believe that this causes a significant gap in the foundations of mathematics. So mathematics lives in this duality between definitions and proofs, and definitions are responsible for the great diversity of mathematical subjects. Then this part is missing. We don't have a good understanding of this, so at least half of mathematics. So our conception of definitions. Well, what would we could call the standard theory of definitions, right? In the standard theory of definitions, definitions are syntactical abbreviations, which can,
Is it, I mean, I already talked to you a lot about this subject, so it's more clarification than anything else, but it's you said that mathematicians don't know about what is definitions, but I mean, this needs to be a little more qualified, because books of mathematics are filled with lots of definitions, right? So in a sense, they are doing definition, but not completely, right? So there is something lack about this definitional practice, because I mean, there is something resembling definitions that occur in the mathematical practice. It's just that it's not enough in some sense, right?
Yes, it's a kind of self-consciousness that is at issue, right? You can be you can have a rational person that is not self-consciousness about its rationality. He is perfectly rational, but when you ask him to explain what in what consists his rationality, maybe he cannot give an appropriate answer, proper answer. So why this defines what are you doing, why this defines anything, in what sense? So this is more abstract, second order kind of question, right? And the standard theory of definitions, we could say, is or this standard conception of definition is a syntactical, we could say, a syntactical conception of definitions. Definitions are dispensable syntactical abbreviations, right? You just use a name in the place of complex expression. You are just abbreviating things. Bertrand Russell, in his, I think it is in the Principia Mathematica, has a very peculiar passage. It goes more or less like this. At page 3, he says that definitions are understood in the standard sense as syntactical abbreviations of, and they are in principle dispensable syntactical abbreviations of complex expressions. And at page 4 or 5, he says definitions are the most important part of this book, the Principia Mathematics. Well, one must choose between being dispensable or the main thing. One cannot have both, right? Of course, it's a book on the foundations of mathematics. It's not proving new theorems, but yeah, in a sense, definitions are the most important part of the book. Right? He's showing how the mathematical notions can be defined in terms of logical notions, and then everything works out with appropriate definitions. So, yeah, please.
Oh, sorry. Oh, you got it. Isn't there a play on dispensable there? That is, when he says dispensable the first time, he's meaning we can always replace. But when he says it's the most important thing, he's saying the act of being able to make these replacements is the most important thing.
Well, maybe, but yeah, but definitions in the Freudian sense, in the logicist project, generate knowledge, right? To define a number, the definition of a natural number in the Freudian sense, and I think in the sense of Russell also, is knowledge. So a number now is this stuff, this logical stuff. So it is not dispensable in the sense that if you replace it, you lose the number, right? You have the definition of number 1, for example, and if you replace 1 by its definition, you lose the number. So you lose mathematics. When you make the replacement, you go back to logic, and then mathematics is, in a sense, lost. Right. If you replace the definition of the natural numbers, the natural numbers by its definition, you have a tautology, but you are not talking about numbers anymore. So I think that, I don't know, but I think that Russell means this when he says that definitions are the most important part of the book, is that mathematics comes in through the definitions. It is otherwise it is not foundations of mathematics. It's just the exercise of logic. So if you dispense definitions, you lose mathematics, so they are not dispensable. But well, here I am working out a different theory of definitions. This is not only Russell. Curry also, in his book Foundations of Mathematical Logic, he has a small section called Theory of Definitions, in which he says exactly this. They are dispensable syntactical abbreviations. Well, the point of this course is basically to explain, right, this interpretative conception, the semantic conception of definitions, and it's a little bit involved, so it will take some time, but we can start saying some important things. A proof is always a proof of a proposition in mathematics. Here, a definition is always a definition of a predicate, right? It's not that we do not have other kinds of definitions. We do have other definitions of other kinds of objects, but I'm claiming that all mathematical definitions can be viewed as definitions of predicates. There is a kind of reduction here, right? But well, when you define, for example, you can ask, when you define an object, the number 1, for example, well, this is, you can say, oh, this is not a predicate. Yes, but we can view this as a definition of an appropriate predicate. What predicate? The predicate of being one. Just like Quine and Russell eliminates the use of proper names, we can, in terms of predicates, right? Quine famously eliminates Pegasus in terms of Pegasises. So here we are doing a similar movement. So a definition will be always thought as a definition of a predicate. And a predicate, we say that a predicate is defined whenever it is singled out as the interpretation of a new symbol. So this is manifestly an interpretative activity, or this has manifestly an semantic dimension, because the predicate is the interpretation of the symbol. So we have a relation between a symbol and a predicate. This is not just symbolic. It lives in the semantic layer. So this thing will come out. I view mathematical theories as double layered. A mathematical theory is not conceived here as just the exercise of a symbolism. A mathematical theory has a symbolic dimension, but also a semantic dimension. When you give a theory, you give not only rules for writing the right expressions, you must also give rules for interpreting these expressions. So giving a theory is giving a syntax and a semantics, right? So I think of a theory as a mathematical theory as double layered. You cannot just write down axioms. You are not giving anything, because you must give the rule for the interpretation of the axioms. How can I make sense of this? Right? So this will appear eventually. So a predicate is defined whenever it's singled out as the interpretation of a new symbol R. And there are two separate issues here. What are the possible interpretations of R? And what could count as an ambiguous selection of one of them? Because, well, there is this university issue, right? Definitions are supposed to be unequivocal. They are supposed to be unambiguous. They're supposed to define uniquely something, right? So when we say that a predicate is defined whenever it is singled out as the interpretation of a new symbol, we have this two issues. What are the possible interpretations of a predicate symbol? What is a predicate? And what could count as an ambiguous selection of one of those predicates, right? How can we select an interpretation of a symbol? The answers to both issues depend on how we conceive the theories in which definitions take place. So these questions naturally leads us to the discussion of theories, of mathematical theories. Well, a definition is always take place within some theory. So this is part of our conception of mathematics as a theoretical activity, not as an intuitive, perceptive activity. So mathematics is not like drawing, but it could be, right? It is a reasonable conception of mathematics, that it is perceptual, that we have ad oculus demonstrations. And we had in history this ad oculus conception of mathematics. Well, you make a figure and look at it. This is part of the proof. Now, mathematics, Euclidean mathematics is full of drawings. But you take a book from Bourbaki, for example, and there are no pictures in the book. They say down to Euclides, down to geometry. Now mathematics is primarily arithmetic, or primarily set theory, not primarily geometry. There is an inversion of the basic mathematical discipline around the 19th century. Arithmetic takes the place of geometry as more fundamental. This is a revolution in mathematics, right? So now we are in this theoretical tradition of mathematics, and definitions take place in theories. So interpretation of R is part of the interpretation of the theory. So the semantic layer is important, right? To this day, right, I am saying and emphasizing this, to this day, it is not trivial to convince a mathematician that a language has something to do with mathematics. Now, why language? I choose mathematics because I am not good at language. Right? I like to make operations, not to interpret some poem, some poetry. So continue with our conception of definition. You can stop me at any time, okay? A mathematical definition of a predicate is always given by a formal theory, right? In terms of other predicates and with respect to a class of admissible interpretations. So we have a formal theory with some symbolism, the other predicates of the theory, and the other logical symbolism, whatever it is that the theory might display. And we have the semantic dimension of the theory, right? There is nothing in the symbolism that forces you to interpret it in some way or another, right? There is nothing in this symbol forcing you to interpret it in the way we interpret it as a universal quantifier. Okay. This is a separate dimension of the theory, right? And it is based on what I call deep semantic agreements. We have some deep semantic agreements on how can we interpret our language, right? It is a task of the foundations of mathematics to bring these agreements, these implicit commitments to light. Yeah. Yeah, the word formal is really dispensable here, but because I didn't explain it what I mean by this, but I will work, but yes, this is pointing to something that will come afterwards, that I will work in a logical framework, yes. So formal theory will be in a formal language, will be given in a formal language. But the fact that it is a formal language does not mean that it does not have a semantics.
Sort of in the model-theoretic logics theory, that you have the logic and the semantics without necessarily having a syntax.
Yeah.
Yeah, I mean that, right? That's how that book starts off. So
yeah, yeah, that's how my book starts. Yeah.
So if you want to save it for later, that's okay. Are you thinking about a difference between a mathematical definition and a logical definition? Because you gave it as an example of what you usually accepted as a logical notion and not a mathematical notion. So is there a difference?
It is a very good question. I am still thinking about it, but I am not making a difference.
Okay.
That means that I'm not making a qualitative difference. It may have we may distinguish between definitions of or interpretations of logical notions and interpretations of mathematical notions in terms of degree. The logical definitions are part of the more basic agreements, and then mathematical definitions can be less basic. But part of the discussion is what are the most basic, the deep agreement behind the semantics. And there will be logical and mathematical notions in the deep agreement, let us call it this way. The notion of natural number, the standard natural number, is part of our deep agreement, semantic deep agreement in mathematics, right?
This is very interesting because it can gives rise to a different kind of logicism as well, at least in terms of definitions. I don't know if you think about the difference between a logical proof and a mathematical proof. If there's also no difference, then you have a different kind of logicism.
Yeah. We will distinguish at some point logic and mathematics. This is important, but at this point we have two undefined terms. We have not defined logic and we have not defined mathematics. So we cannot distinguish between them because both are undefined. Right. But at some point I will say some words about that. So this presentation is focused on formal theories ruling large portions of the mathematical activity, like the usual theory of sets. Well, let me say some words about this. I have said that mathematics is here conceived as a pair of practices, the practice of proof and the practice of definitions. But this practice must be ruled. What do I mean by practice? It's not some random activity that anyone might like to play. It is a ruled practice, right? So mathematics, so the practice of definitions has some rules, as the practice of proofs have some rules. So and this will lead us to a normative conception of mathematical theories also, right? Mathematical theories are conceived as norms for the mathematical practices, right? When we write down a theory, which is just not write down the symbolism, but also the rules for the semantics, the semantic rules for the theory, we are writing explicitly the rules for the practice of proofs and the practice of interpretations, which is the practice of definition. We will distinguish between interpretations and definitions, but they are very much closely related. But when I say that mathematical theories are norms for the mathematical practices, I don't mean that these norms are historical accident or irrational. So I will say more words about that. So without no natural status. So we will enter that point. So we must be careful on this. So part of our main problem, leaving aside the issue of which class of interpretations should be preferred, can be reformulated as follows. Which formal theories could count as extensions of set theory obtained by the addition of new defined predicates in terms of the old predicates? So here, well, many things must be said about this. So we view mathematics, or at least formal axiomatic mathematics, as living in some extension of set theory. So we start with basic set theory, and then we add definitions to it. So we are following a path similar to, for example, Bourbaki. So Bourbaki, book 1, that's the theory of sets. So it gives you the basic formal language of mathematics, which for them is a version of Hilbert's epsilon calculus. So this is their logic. And then they built the basic set theory over the top of this logic. And this is book 1. And then book 2, algebra. Then they start with definitions. Definition of monoid, definition of group, definition of ring, of module, and the sub-definition, exact module, and stuff like that. So we start with a basis of set theory, and then we gradually add definitions to this basis, right? And this is, of course, open-ended, right? You can add another definition today, tomorrow, etc. But we will always be working on some extension, possibly a countable number of definitions can be added. And my question is, what kind of, there are many different kinds of definitions of set theory. Which ones are definitional extensions? Extensions obtained by the addition of definitions only, not by the addition of, for example, a new axiom, completely different axiom or stuff like that. But so what could count as a definitional extension of set theory? This is our question. There are some, according to the standard theory of definitions as syntactical abbreviations, we have a standard answer to our question. So definitional extensions of set theory are what are usually called in textbooks extensions by definitions, by explicit definitions. So you have a predicate symbol basically abbreviating a formula. And you can add the axiom saying that this predicate is equivalent to the defining formula, to set theory, and then you have a definitional extension in the usual sense. My point is that is not the right theory of mathematical defining. Right? Not only because it is syntactical or language-based, instead of interpretative semantic. It is not only the issue of the nature of definitions, which is not syntactic but semantics, but also, more importantly, because many mathematical notions are undefinable in this sense. Professor Baldwin is talking about really mainstream core mathematical notions of geometry, classical geometry, and sometimes at some point omega logic or L omega 1 omega will come into the scene. And this also destroys this view. But I am thinking of some meta-mathematical notions and also mathematical ones that are undefinable in the standard view of definitional extensions. So, for example, one usually says that the truth predicate is undefinable. This is a very standard theorem in mathematical logic called Tarski's undefinability of truth theorem. So in the usual view of definitional extensions of set theory, if we answer this question as saying, well, a definitional extension of set theory is just the usual definitional extensions in textbooks, the abbreviation of formulas by new predicates, then the truth predicate is undefinable. That does mean that it is not a bona fide mathematical or mathematical predicate. No. We use it is a very important predicate for mathematics. We will discuss this. Mathematics is not only a practice or an arbitrary game. It is aimed towards truth. So that's why we have a mathematics department here and not a chess department in the university. It's because mathematics aims at knowledge. University is about knowledge, and mathematics is part of this, a standard part of this, of our knowledge tradition. So truth is very important for mathematics, but also the notion of theorem. This is a bit more subtle, but the same theorem says that not only truth is undefinable, but validity is undefinable. If you look at Gödel's first incompleteness theorem, you can read it as showing that theoremicity, the property of being a theorem, is not representable.
Rodrigo, thanks. But you consider that we can understand knowledge in only one definition or in the relation between definitions? For Henri Poincaré, for example, or Reichenbach, definitions are freely choices, but between the relations, in the relations between the definitions, you have axioms. Maybe for a neo-Kantian guy, you understand this like a synthetic a priori knowledge. Né? But for one empiricist, all is definitions. So where we have the knowledge in your view?
Maybe we don't. Knowledge here is has the role of an ideal. Mathematics is aimed towards knowledge. So maybe we never reach knowledge, right? It is, in some sense, a classical rationalist view, right? But I will talk more about that then. But for example, so theoremicity is also undefinable by the same. Yeah.
But you're going to provide a sense in which they are definable.
Yeah. I will show that in my conception, all of this stuff is definable. They are all bona fide mathematical definitions. But we have to change the semantic agreement. It cannot be plain first-order logic. This is where the omega structures come in. So, well, the notion of definition itself is undefinable. This is also a famous logical theorem, the undefinability of definability, right? But it does not mean that it is, in some sense, a cracked notion, right? It is a perfectly good mathematical or meta-mathematical notion. We talk about the definable sets, for example. We even have some theorems about them. But we can have a theorem, for example, that we cannot prove in ZFC that we have a definable well-ordering of the reals. Right? You all know what is well-ordering. It is an ordering, total ordering, such that for every non-empty subset of the ordering, we have the smallest guy in this non-empty part. We can prove by mathematical methods, forcing, that it is consistent not to have a definable well-ordering of the reals. But this is an impossible statement because we cannot even say that because we have not a definition of definable or undefinable. What we prove is another statement which says that we do not have an ordinal definable well-ordering of the reals in some model. And ordinal definable is definable. But then we see definable as a particular case of ordinal definable, because it is. It is a perfectly good mathematical notion, but nevertheless, it is not part of the usual theory of definitions. It is undefinable. The proof that it is undefinable is very easy. It is similarly to the truth and the theoremicity and definability, which is based on the liar paradox. The undefinability of definability is based on Richard's paradox about the smallest undefinable ordinal. So if definability were definable, we would have the definable ordinals, but the definable ordinals cannot be all ordinals because we don't have enough formulas for all ordinals. There are more ordinals than language. And so if we have we would have undefinable ordinals, and then we would have the first undefinable ordinal. Oh, but that is just defined. And this is a contradiction. So definability itself is undefinable. But that's a problem with our notion of definable, not with definability itself. Well, the replacement schema. This is, we talk about this as it were a proposition, just like the induction schema. Well, it seems like a proposition. We do not seem to have a priori problem with this proposition. What is the replacement schema? Is the statement according to which if we have a set and we replace its elements one by one, then the image of this replacement is also a set, right? This cannot be formulated as a single proposition in a standard plain first order logic. It is a schema, which means that there is no proposition corresponding to this. Like the induction schema, there's no single proposition corresponding to the induction schema in the plain first order setting. And the last one, the notion of a standard natural number. This is undefinable by compactness. In the first order logic setting, we cannot define this, but it does not mean that it is not a bona fide mathematical notion. On the contrary, it is a basic mathematical notion, but we cannot define it. And all the other previous notions can be defined in terms of this notion. So this is lacking. This is the fundamental notion that is lacking. If we introduce this notion in our system, we can define the others in omega logic, in an omega structure setting. So, well, that the notion of standard natural number is undefinable never occurred to mathematics in the millennia tradition. It is something of the 20th century only. If you were asked to explain this notion, right? You would say, that as we have been talking about, well, there is nothing much better than to say that a standard natural number is 1, 2, 3, 0, 1, 2, 3, and so on. It is the numbers that you get, but by the process of iteration itself, which is a basic process. And we cannot give a first order definition of this. So, well, it is a consequence of the compactness theorem of model theory. You can discuss this. I will talk about compactness later. So, well, some more philosophical remarks to clarify our position. So we will talk about mathematics, and then we have to we will talk about mathematical definitions, and we have seen that we must talk about the mathematical theories, the theories in which definitions take place. So we cannot answer the question, what is a definition, without answering the question, what is a theory? What is a mathematical theory? So those questions are very closely related. So theories for mathematics as a whole are conceived as instituted norms for the mathematical practices according to the normative account we are proposing. So mathematics is, in the real world, let us say, a bunch of practices of proofs and practices of definitions. But these practices are not random practices, but they are ruled. Right? Any serious activity is committed to some norm. So the mathematical theories provide these instituted norms for the practice of proofs and definitions. But this does not come from the heavens also. The theories are not falling from the sky to us. They are the relation of between the theories and the corresponding practices is twofold, right? On the one hand, mathematics is a historically instituted plurality of practices, right? In the real world view of mathematics, so it is everything, as Kant says in the beginning of the Critique of Pure Reason, every knowledge starts with experience, but this does not mean that all knowledge is grounded in experience. So mathematics is not different. It starts with human experience and human mankind problems of survival and stuff like that. So we have a historically instituted plurality of practice, so that a mathematical theory, a theory for mathematics, is a formal axiomatic image of this practice. So when we make the rules behind this practice explicit, we have the theories for mathematics. The theories for mathematics can be seen as obtained by making the rules explicit. And to make the rules explicit, you must write them down. And you must write them down in some specific language. So that is our point of the 20th century mathematics. Language becomes important. For the axiomatization. Which language we will use? You have to use the microphone.
Do you consider this activity of laying down the norms as doing mathematics?
I would say that it is part of the foundations of mathematics or the meta-mathematics, but the part of gaining self-consciousness of our rationality. This is what we usually call logic, right? It is our semantic self-consciousness.
Okay.
Right? But of course, logic and foundations of mathematics and mathematics are overlapping very much. So it can be seen also as part of mathematics. So on the one hand, we have this down-to-earth, a bunch of practice, and we make its rules explicit, and so we have the formal theories. So the theories are derived in some sense from the practice. On the other hand, being a norm, a formal theory that is a list of formal axioms and rules. This is the symbolic dimension, a list of formal axioms and rules, but it is not enough. Along with the appropriate interpretative agreements concerning its language. So this is the semantic dimension. We have the symbolic dimension and the semantic dimension. Well, this is a formal theory, a norm. This is constrains the practice of those who claim to be doing mathematics. So if you claim to be doing mathematics, you must conform to the norm. No, you cannot do anything you want. You must follow the rules. If you want to play chess, you must follow the rules. This is so the theories for mathematics also constrain the practice. So the rules, so this is the two-way relationship between practice and theory. So it is something, how can we came out of this circularity? It is by a process. It is a historical process. So we have a practice, and then this practice gives you rules, and these rules constrain the further practice, and then the practice may change, and then we have new rules, and so on. Well, but that does not mean that mathematics is a matter of historical accident. It is not. So, however, to say that the rules directing mathematical practice as a whole are historically instituted is not to say that they are a matter of historical accident. We are not defending a form of historicism. Rather, we think of the instituted principles for all of mathematics as a purposeful outcome of a rational interaction, not as an arbitrary language convention with no cognitive status. So this is rational, classical rationalism. This is the essence of Platonism, right? Platonism has acquired a different sense these days, which means that we have this realm of detached objects, but it need not be understood in this way. So we can understand the essence of classical rationalism, which is not restricted to Plato, but also to Aristotle, as saying that our practices are aimed at virtue, or at the good, or at the truth, or at knowledge. So the mathematical practices are not a matter of historical accident, are not arbitrary rules, are not some mere game, mere convention, mere language convention, human convention, right? It is part of the university, so it is aimed at knowledge. The relationship between mathematics and its history is more nuanced than that contained in the radical historicist thesis, because the radical historicist thesis leads us to relativism, which is not okay. I am making a lot of philosophical remarks here because logic and the foundations of mathematics are not just purely mathematical stuff. Like it is, so we are in an intersection between mathematics, logic, and philosophy. So we have to understand the philosophical standpoint. We are trying to give a formal formulation, because otherwise we would be giving some sort of empty formalism, right? It is, we can make an analogy with mathematical physics, right? The foundations of mathematics is some kind of mathematical philosophy, right? It is a bit strange to do mathematical physics without being engaged with physics. So it is a bit strange to make foundations of mathematics without being engaged with foundations, with philosophy. Logic was philosophy from Aristotle until Freire. So yeah, and until maybe Quine. So this marriage between mathematics and logic is quite recent. It's a quite recent thing, right? So we have to be careful not to confuse things. So it is important to give this context. Just like we can do mathematical physics, just write down some Schrödinger equation and study the spectrum and so on, without never speaking the word quantum physics or something like that, but it is a bit strange to do that, right? Why? So this case is analogous. So on the one hand, mathematical practices are aimed at understanding shared notions, and this is the stuff we were discussing, that due to our cognitive condition, we happen to have touched upon through human history. So shared notions are, the mathematical notions are notions that we share. This means that mathematics lives in the common ground, not in the private language, but in the common ground, right? It's the common part, it's the shared part of our communication, right? It's in there, lives there, the shared part of our cognitive, in the shared part of our cognitive life. So mathematics are aimed. Now this is aimed at an ideal. This is classical rationalism. And the ideal here is the ideal of knowledge, of understanding notions, right? So mathematical knowledge is the knowledge of these notions, of mathematical notions. So on the other hand, the purpose of a historically instituted axiomatization for all of mathematics is to guarantee that the corresponding collection of practice can count as a quest for knowledge of the shared mathematical notions, right? What can count as a quest of knowledge? It's not an arbitrary game, but some specific practices. So this is the rationality behind the rules of mathematics, right? So by a shared mathematical notion, like the notion of a standard natural number, we mean any metalinguistic agreement. So it is an agreement, which means that it is common. It is in the common ground. The common ground is where we have agreements. We mean any metalinguistic agreement for interpreting a mathematical language in symbolism. So this is my way out of the mental. Mathematical notions are not mental objects, but agreements. Basic agreements. All communication is based on some agreements, on how we understand the language. When we learn a mathematical language, we learn not only how to write syntactically correct sentences and proofs, but also a prescription for adequately interpreting the appropriate expressions. We learn not only writing, but understanding, but interpreting, but giving meaning to it. It is important to remark that we can, in some cases, under favorable conditions, indeed learn a prescription for interpreting a given discourse. That is, our agreements may fail. They are not infallible capacity, but it is a self-correcting activity. If we want to make an agreement, right? Let us agree to meet at the Institute of Physics. So this may fail for several reasons. We may not know where the Institute of Physics is. We may not know what time to be there. But this can be corrected. We have a self-correcting practice. So I can ask, well, this agreement is a bit vague or ill-defined. I must ask, what time am I expected to be there? Where is it? And we can try to explain, well, I don't know where the Institute of Physics is, but I know where the Fefeleche is. So can you give me directions from Fefeleche to the Institute of Physics? So we can refine our agreements. There may be recalcitrant failures, right? Maybe we will never, we enter on this dialectical process, let me say, and the problems, the contradictions, let us say, may not be overcome. Maybe we cannot reach a successful communication. In some cases, our agreements may fail. But under favorable conditions, we can indeed learn a prescription for interpreting a given discourse. My point is that the standard natural numbers is just one of that kind of successful prescription. We have a successful agreement to understand the standard natural numbers, and this is an irreducible agreement, right? So it cannot be defined in other terms. Well, now we are back to some more mathematical issues after this philosophical detour. I have condensed the philosophical part to a bare minimum, let me say, right? So there's more than 40 pages on this part only, but just to say some words. I have given this background. So back to the point of the interpretation of the predicates, the possible interpretation of the predicate symbols. Well, the possible interpretations of a predicate symbol depend on what could count as an interpretation of a defining theory T. So all definitions take place in a defining theory. So if we are, the role of the defining theory is to select to identify the appropriate interpretation of R. This is what it means for T to define R. T defines R if T identifies the appropriate interpretation of R without ambiguity. But the appropriate interpretation of R will be part of the interpretation of T, because R is part of T. T is not one thing and R is another thing separated from T. R lives within T. So just like lines live within geometry. Therefore, the possible interpretations of R depend on the possible interpretations of T, hence on the admissible interpretations of set theory, because we are concerned with T's that are extending set theory, because I am concerned with mathematics as a whole, like this Bourbakist architecture, in this Bourbakist architecture of mathematics. So all mathematical definitions can be introduced in set theory. For example, take your favorite mathematical structure, say groups. This is introduced as a predicate in set theory, saying the predicates say that what it is to be a group, the predicate of being a group. So this is a class of structures. The predicate defines a class. So let us separate two pending issues to be addressed. What is an interpretation of a theory defining a mathematical predicate, and which ones are admissible? What kind of thing is an interpretation of T, and which ones correctly interpret T? So you can say, oh, the interpretations of T are the kind of thing that is an interpretation of T is a first order structure, and the correct ones are the models of T. This is a standard answer to these questions. So what kind of thing is an interpretation of T? A first order structure. Which ones correctly interpret T? Those first order structures which are models of T, which satisfies the axioms of T. But this is an agreement. This is not, you are not forced to this kind of interpretation, to this semantics. So there is nothing in the symbolism that tells us that we must interpret our theories in first order structures. We can do that, but it is part of our semantic agreement to when we learn this language. So there is a lot here that is very much new in mathematics. This distinction between the semantics and syntax. This is 20th century stuff, but we will rely on that. So we have what I call an interpretative basis. So it is the answer of the first question. What kind of thing is an interpretation of T? The first interpretative basis is just what I told you, the non-empty first-order structures, for example. I will go back to this point in the next talk, but let me just, to finish, just say that the preferred interpretative basis, in my view, is given by the class of omega structures. So there is a distinction here. We can interpret our theory in terms of plain first-order structures, but we have another option. We can, and possibly others, of course, right? But I will consider just two interpretative bases. We can consider many other things. And the second interpretative basis is given by the class of all omega structures. So here is where the standard natural numbers come in. We take them as God-given in our semantics. Of course, this is not God-given at all. It is just given in our agreement, in our basic semantic agreement. So it is part of an irreducible part of mathematical semantics to include the natural, standard natural numbers. I have some quote of Hilbert at some place that it's here. That let me finish with this quote by Hilbert. Why introducing the natural numbers as a basic part of our semantics, irreducible part of our semantics, which is available to us? No more than any other science, right? Hilbert views mathematics, of course, as a science, not as a kind of art, right? Hilbert knows, and he is one of the main figures behind the theoretical language-based conception of mathematics, of contemporary mathematics. So no more than any other science can mathematics be founded by logic alone. By logic here, I understand a thing that probably very different from Hilbert, but we can take his words as basically faithful of our position. And so no more than any other science can mathematics be founded by logic alone. Rather, as a condition for the use of logical inferences and the performance of logical operations, as a condition for the use of the formalism. Something must already be given to us in our faculty of representation. I completely disagree. Not completely disagree, but something must already be given to us in our basic agreement. Certain extra-logical concrete objects, the standard natural numbers, that are intuitively present as immediate experience prior to all thought. It is prior to all thought. So it is not a thought. It is an immediate experience in Hilbertian sense. So what is he talking about? Well, in order to work with the syntax, we must have this concrete objects that constitute syntax. We must have the knowledge of the symbolism of following a logical operation, of the process of iteration that is behind the notion of formula, that is behind the notion of deduction. This he calls extra-logical concrete objects, can be just the standard natural numbers. And not logic alone, that is. I understand this as not plain first-order structures only, but omega structures. Right? Well, I will leave it at that point. Maybe you have some time for questions and remarks, and we will continue tomorrow.
Okay, thanks. Thank you very much. It was very interesting. Let me just start from this last quotation, which is very telling about the whole approach. So, I mean, a first comment is that this is just very full of Kantian terms, which are clearly part of the knowledge of the time, but was not completely subscribed by Hilbert. Representation and concrete and experience and all these things.
It's very Kantian.
It's all very Kantian. So, but he had this idea since before the proof theory and his reduction and the Hilbert program. But then he moved towards, I mean, this idea that these symbols actually are a form of arithmetic. And he tried to axiomatize this and to reduce everything to that, and we know it doesn't work. But his idea was, and that's the finitist perspective, and that you don't need all the omega sequence, but just a fragment of this. So the question then is, why do you think that we can, on the basis of what you're telling, which is basic agreements about our doing mathematics, we can do this jump from finite to already infinite? And how can we agree on that? Because, I mean, one possible objection is, well, look, in the end, of course we agree, but we all have, we are finite objects, we are finite beings, and so the thing on which we agree is always so finite that we don't really capture the omega sequence in itself, and then you're back to the, I mean, compactness problems of non-standardness of arithmetic and so on and so forth, of first-order logic.
I can give you one answer, which is Brouwer's answer. It is because we agree, not really Brouwer's answer. Brouwer's answer would be because we have the intuition of the process of iteration, which is a single process, not an infinite process, not an infinite number of things. Yeah, even more Kantian. Yeah, we have. So I would adapt his answer to say that it is one answer. It is because we can agree on the process of iteration. What is the basic process of iteration? To add one object to a given already obtained sequence of objects. This is one kind of answer. The second answer is that because being a standard natural number, is being named the property of what is a standard natural number. Well, we don't care what exactly the object is. Well, we have discussed this with John up to isomorphism. So to be a natural number is to be named by an appropriate name from a countable stock of names. And these countable stocks can be obtained as the process of symbolic iteration, which is a single process also. So to say that our agreement in this case fails constantly is to say that we must have an ambiguity at some point. Either we have an ambiguity on what can count as the names, the numerals, or the names for the numbers, or we have some irremovable ambiguity on the naming, on the pointing from names to numbers. And my argument is that we don't have an ambiguity in either case. The numerals are just the plain process of iteration, a la Brouwer. And we have this agreement on the process of iteration. Otherwise, we don't have an agreement on what is ZF. Yeah, we don't have an agreement on what is a sequence of variables. And so we do not have an irremovable ambiguity at this point, and we also do not have an irremovable ambiguity on the naming part, on the pointing from numerals to theoretical objects. Why? Because it is part of our semantic experience that Lina has already acquired when she attributes the barking of the dog to the dog. It is the assignment of a symbol to an object. It is part of our cognitive experience, long acquired long ago, right? So that would be the answer. So we can remove the infinity by the process of iteration.
I have a question and one comment regarding this, which is maybe there is something, yes, excessively Kantian here, and in this sense, excessively like leaving the problem behind, right? Which may be recovered by considering a more Hegelian kind of aspect to it. I'm not kidding. And the sense is basically that, and maybe the fundamental idea is that we have an agreement that we should operate as if we have an. And by doing this, we are leaving the further disagreement to operate itself, right? Like, so it's gonna appear later on. But then my question is, you connect when you talk about theory and a concept within a theory, you say that the concept is dependent on the theory, right? So you are kind of arguing that the mathematical contexts are always theory dependent, or is there any sense of being open to be theory independent, like in Euclidean kind of style, which I think is something to be recovered? You know, like I think we discussed this a little bit. I have been reading a little bit about Kit Fine and how we should understand definitions also as discussing the essence of the thing, instead of putting it into these too much in this holistic kind of framework.
Thank you. Hilbert surely is very Kantian. Here he is describing meta-mathematics. He is very Kantian about meta-mathematics, right? And yeah, Hegel have some role to play, but I am neither, right? This view is basically rationalist, right? Hegel is a historicist, and but yeah, you were right. Yeah, in a sense, well, there are many interpretations of Hegel, but in a sense, he's a Platonist. In a sense, he's a Platonist because he puts his reason in the direction of history, but it is unclear whether the ideal comes from history or yeah. I think that I have not gave up the idea of truth and justification and knowledge, and mathematics is aimed at that, even if it will never achieve that in absolute sense, right? We may never achieve absolute justification because we always have some hypotheses in our justifications. So but with respect to your question, yes, the concepts, I have not said the concepts, but the interpretation of the predicates. The mathematical notions are in a sense theory independent, because the mathematical notions are the semantic agreements, so, or the content of the semantic agreements, right? Behind the when we give a theory, we must give the semantic agreement behind the theory, or how are we supposed to interpret this theory. And this is the mathematical notion. So when I give you a theory in with the theory that I will give here, ZFC-N, I have a semantic agreement for interpreting N. This semantic agreement is the notion of standard natural number. So it is, in a sense, independent of the theory, because it is an agreement behind the theory, the interpretation of the theory. Yeah, but I said that the predicate, the interpretation of the predicate, this is a different thing from the mathematical notion. One thing is the mathematical notion, the other thing is the interpretation of the predicate. So the mathematical notion is the semantic agreement itself. The interpretation of the predicate is the interpretation that we give after this semantic agreement. So I will try to make this distinction clear afterwards. Oh, John.
So when you gave this list of 5 things that are not definable, it wasn't quite clear to me what the languages were, and later you said it's very much language dependent, and that then, if I look at the notion of standard natural number and I say I'm working in ZFC, then I will read in any set theory book that omega is definable. And so why is this an example of something that's not definable? Wait, are you referring to in the language of just successor or something? I mean, what is the, because if you say I'm going to take a non-well-founded model of ZFC, then I say you've moved up a level in my hierarchy. ZFC does have a definition.
ZFC does have a definition of omega, but it's not a definition of standard natural number, because we can have non-standard natural numbers. Yeah, that's it. You are right. We are moving to the semantic layer, but the semantic layer for me is part of the theory. We are moving to, yeah, of course, we are moving to the interpretative basis. Yeah, the meta theory is constituted by the semantic agreements that we have. This is my meta theory. It is the final meta theory cannot be a theory. Cannot be cannot be a theoretical construct, because that would require another meta theory for that theoretical construct to make sense. So the final meta theory, the ultimate meta theory, is part of our practice, and it's part of our practice of communication of the basic semantic. What I'm talking, what I'm saying is the basic semantic agreements. So yes, in set theory we can, in ZFC for example, we can introduce this ZFCN with the same axioms. The difference is in the interpretation. Yeah, you can introduce the same definitions in ZFC. You can. My point is, the definition of standard natural number is in some sense in ZFC, but it is an schema. This is the definition. Yeah, but this is different from the least inductive set. Well, these are different in plain first order logic, but in omega logic It can be, they can be equal. So the definition, in my view, the definition of the standard natural numbers is this schema. My point is that schemas are bona fide definitions. This is a perfectly good definition. It is not a first order logic definition. All these things can be seen as schematic definitions, like that one. This can be seen as a schematic definition also, or an infinite definition in this sense. Please, John.
So as I started with, I open Kunin and I read a I open Kunin and I read, here is a definition of and you say it's not a definition.
No, it is a definition, but it is not a definition of standard.
Well, that's not what Kunin says. He doesn't have a, so this word standard is something you're adding that a set theorist doesn't recognize. Is that it? Yeah, okay, and so for all of these, right, so but it's, right, so it's very definitely a different, well, you've added the word standard, and it means something, while a person normally reading a set theory textbook does not understand it.
Yeah, you can make a, I will try to explain that.
Yeah.
Me and John are discussing this for months.
Yeah. Right, yeah.
You can make like a mental experiment of saying like, all right, so I have a definition of omega in my meta theory, but in this very same meta theory, I can build up a process in which a model believes itself to be talking about the standard numbers and yet not being actually talking about my standard numbers. So you can make the transcendental jump that, well, maybe myself, my own omega definition is non-standard. That's what I think this is an important point, like almost like a phenomenological kind of point, like you make a definition, but you can, in your own house, in your own meta-theoretical environment, make a experiment where one thinks it has the natural numbers, the standard natural numbers, while not having them. So I can believe maybe I am myself doing the same, right?
Yeah, that's because that's the reason we need a basic agreement, right? That if this can happen and we have indeed no shared notion of standard natural numbers, indeed our communication fails partially. It fails because you have one notion of formula and I have another notion of formula, for example, or of language or whatever. So Yeah, you were right. Yeah, if we, it is, this does not capture this, and it is irreducible. There's nothing we can do except to basically do like Kronecker. It is God-given. But or, well, not God-given, but we have to suppose that we have this shared structure, this shared agreement, and the shared agreement is not an infinite agreement. It is an agreement about the process of iteration, right? The agreement is not about this infinite list, but how it continues at each point. So, do we have a shared notion of iteration? Yes. I am talking about this notion. You have this, you put this. And then we have this, put this. This is something that we share. Yeah. This is the notion of natural number, standard natural number. This is what I call the notion of standard natural number. Our sharing of this. It is not a mental stuff because it is shared. And it is not infinite because it is the iteration itself. Well, yes, it can be something like the part that it's intersubjective.